In this video lesson, I will be discussing topic 2, classification of differential equations. So recall that a differential equation is an equation that contains derivative. And the unknown of a differential equation is a function, and the function depends on independent variables. So first, differential equations can be divided into two types, depending on whether we have one independent variable or several independent variables. The first type, ordinary differential equation. So these are the differential equations. With only one independent variable. So in the previous topic, we have seen several examples of differential equations, and all of them are actually ordinary differential equations because we only saw one independent variable, either x or t. Ordinary differential equations are also known as ODE. The second type of differential equations are partial differential equations. You may be able to guess what these equations are. They are differential equations with two or more independent variables. In this class, we actually study ordinary differential equations only. However, let me give you two examples of partial differential equations. And by the way, these equations are known as PDE. So let's look at an example of a PDE. In this example, we will consider the so-called equation. So say we have a metal plate on the plane. Let me draw the coordinate system like this. With x and y coordinates, and here we have a metal plate with a certain shape. It could be a circle, an ellipse, or anything. So, and say at the beginning, we have certain heat source inside the plate. So you see, the heat will then distribute over the entire plate over time. So what is the unknown here? It will let U, depending on three variables, X, Y, and T. This denote the temperature of the point with coordinates X, Y at time T. So in order to describe the temperature of the plate, we need two components, we need two variables, X and Y, to locate the point on the plate, and then the time as well, because the temperature is changing, and it's changing depending on the location of the point and time. So I won't explain why we have the equation, but it's actually from physics that we have this heat equation. Given by the following: U sub t, this is a partial derivative of U in time, equals to a constant alpha times U sub xx, so partial derivative in x 2 times, plus U sub y partial derivative in y 2 times. And alpha is a constant. And this constant depends on the plate we have, the metal plate, what type of metal we have. And this constant is called the diffusivity. Diffusivity of the plate. So we see that this is an equation that contains derivative. It's definitely a differential equation, but it also is a PDE because the independent variable here are t, x, and y. Independent variable. And of course, the unknown is u. Now let's look at another example called the wave equation. So in this example, we'll look at the vibration of a certain membrane. So say we have a flat membrane like this, and you can imagine this is the base of a trampoline or something. And at the beginning, we give it a push somewhere inside the trampoline, inside the base of the trampoline. Then we see that the trampoline vibrate. And in order to describe the vibration of the trampoline, we use a differential equation called the wave equation. So how do we have that equation? As before, let's consider the coordinate system, x and y, and we describe u, x, y, t. This is to denote the displacement or the height of the point xy at time t. So for each point on the base of this trampoline, we have coordinate x and coordinate y. And when the trampoline, the base here, vibrate, this point goes up and down depending on time. And we denote the height up or down by u of x, y, t over here. Then we have the equation. Very similar to the heat equation, but this time we have second derivative u in t. So u sub tt equal to alpha u sub xx plus u sub y, and alpha is a constant. This is a differential equation. The unknown is u, which depends on three variables, x, y, and t. So we have a PDE, a partial differential equation in this case. For ODEs, as I have mentioned earlier in this class, we will be studying ODE only. PDEs will be for a different course called partial differential equations. For an ODE, we also divide into two types. And we call them either linear or non-linear ODE. In fact, for PDEs, we also divide into linear and non-linear, but it's not the focus of this topic here. There is a definition of a linear ODE. So suppose we have an ODE with unknown y and independent variable x. Then we say that the differential equation is linear. If we could rewrite the equation, we could rearrange the equation in the format over here. We begin with the highest derivative, and then lower derivative until we don't have any derivative in y, and the rest without y we put on the other side. So after we rearrange the equation like that, we look at the terms in front of the derivative. This is a coefficient. This is another coefficient, etc. We have a linear equation if all the coefficients do not contain y. So you see that the coefficients here only depends on x. The coefficient here depends on x, the independent variable. Again, only independent variable in the coefficient. Then we have linear equation. If the equation is not linear, then we say that this is a non-linear equation. So again, let's look at a few examples. Let's consider the ODE. So y double prime equal to 2y prime minus 3xy plus y squared. So furthermore, in order to classify this differential equation, we should rewrite the equation so that all the terms involving y should be on the left side. But actually in this equation, everything contains y. We need to begin with the highest derivative, which is y double prime here. And then the second one, for the derivative, I rewrite minus 2 for the derivative. Next one is no derivative, rewrite here, 3xy, and plus 3xy, and lastly minus y squared equal to 0. Now we see that the coefficient in front of y double prime, it is 1 coefficient. Coefficient in front of y prime is minus 2. Coefficient in front of y is 3x. But here we have that y squared. If you look back at the format for linear equation, we don't see any y squared. You look back right here. We don't see any y squared. So this equation does not follow the format. So as a result, this is a non-linear equation. Due to the factor of y squared. So in a way that this almost follows the format because the coefficient of y double prime is 1, does not have y. The coefficient is negative 2, does not have y. The coefficient is 3x, does not have y. So these coefficients are good, but due to the y squared term, the equation is not linear. Now let's look at another example. Let's consider the ODE. Say y triple prime minus 2x squared times y equal to 3 sine x y prime plus x cubed. Is this equation linear or non-linear? You may pause the video and think about it for yourself first. So to determine the equation is linear, nonlinear, let's rewrite the equation so that all the terms containing y or derivative on the left side and term without y should be on the right side. So rewrite the equation. We begin with highest derivative, which is triple y triple prime, and then the next derivative, second derivative. We don't see any second derivative, so we could write 0 times second derivative. The first derivative, the term with first derivative is right here, and we need to bring to the other side. This becomes minus 3 sine x times y prime. And the next term is here with y. So we have minus 2x squared times y. And these are all the terms involving y or derivative. The last one, the x cubed, doesn't have any y, so we put on the right hand side. Now let's look at the coefficient. Y triple prime, the coefficient is 1. Y double prime, the second derivative, the coefficient is 0. And then the coefficient of y prime is minus 3 sine x. The coefficient for y is 2x squared. All these coefficients depend only on x. There is no y in these coefficients. So we conclude that the equation is a linear equation. So in the next chapter, when we learn about solving first order differential equations, we will see that for linear equations, we have a method to do so. For nonlinear equations, they are more difficult, and we need to study various methods to solve them. In later chapters, when we study higher order differential equations, we won't be able to touch nonlinear equations. We only learn about solving linear equations only. So that's why determining whether an equation is linear or nonlinear is quite important. And this is the end of this topic.